In our next example, we have an oil tanker that is leaking oil in a radius around the ship. A helicopter monitoring the ship measures the radius of the spill to be increasing at 0.32 feet per minute. We want to find the rate at which the area of the spill is growing when the radius is 500 feet. So in this case, I do think it would be helpful to draw a picture and kind of see what shapes it is that we're going to be working with in this problem. So we have an oil tanker. We can draw ourselves a little boat. It's not a very good oil tanker. I guess that's why it's leaking the oil. But here is my oil tanker, and it says it is leaking oil in a radius around a ship. Radius makes me think of a circle. So here we have a circle with our ship right in the middle of it. And let's see, what else do we know here? We know that the radius of the spill is increasing at 0.32 feet per minute. We want to find the rate at which the area of the spill is growing when the radius is 500 feet. So in both cases, we're talking about radius. We're going to need to know what is r. So in this case, r, let's see, what do we know? R in this problem is 500 feet. I know that the rate of change of r, it says the radius of the spill is increasing at 0.32 feet per minute. Anytime you see that those words increasing or decreasing, that should be a really big clue that, hey, we're going to be talking about derivatives here. We're going to identify a derivative here. So this is the derivative of r with respect to time, dr over dt. This is equal to 0.32 feet per minute. And we know it's positive because we're told that the radius is increasing here by that amount. So what else do we need to know here? Well, we're asked to find the rate at which the area of the spill is growing. So we're going to need to talk about the area of our circle as well. So that means we're going to want to know what is A, and then how is that changing, the rate at which A is changing. I'm going to want to know what is dA over dt. What's the derivative of A look like? So the problem specifically asks to find the rate at which the area of the spill is growing. So dA over dt is actually what it is, or what this problem is asking me to find. That's going to be my solution to this problem. But I'm actually not even told what A is. But that's okay, we can find it. We'll get there. We will find it. So I have, in step 1, drawn my picture. In step 2, I've identified the variables that I'm going to be working with, my radius r and my area A, and then the derivatives of each of those variables and how those relate to the rates that were given to us. Step 4 says, okay, now we need an equation that relates our variables. In this case, our variables are the radius r and the area A. I think about the area of a circle. Area of the circle that we're working with here, because we're specifically talking about area, is A equals pi r squared. Now, if I want to, I can actually use, before I take derivatives or anything else, I can actually use this equation to solve for A. So let's do that really quickly here. A is equal to pi, remember that's just a constant, 3.14, times r squared, that's going to be 500 squared. So let's see, 500 squared times pi. I ended up with an area of, let's see, 785,398.16. So if you wanted to know what the area was, there it is. It's 785,398.16. But that's not actually what the problem asked us to find. We wanted to know what is dA over dt. This is the piece of information that we're going to be solving for. So we're still going to be working with the area formula of a circle, so I'm going to write this over here now. A equals pi r squared. This is the equation that relates our variables. And I'm going to take the derivative of this equation with respect to time t. So I want to take the derivative with respect to t. So the derivative of a, well, that's just 1. But again, I'm taking the derivative with respect to time t. Area is changing with respect to time, which means area is a function of time. So that means I need to multiply by dA over dt is equal to derivative of this right-hand side. Be careful with this right-hand side. Remember, pi is a constant. Pi is 3.14159 blah, blah, blah. It's that big, long, infinite number. But what that means for us is that we have a constant multiple here. It actually means we're not going to need to use the product rule, which is nice. It saves us a little bit of time. The derivative of r squared, though, that I can use my power rule for. So the derivative of that right-hand side is going to look like 2 times pi times r to the first power times, again, r is changing with respect to time. The radius is changing as time moves forward. So that means I need to multiply by dr over dt for my implicit differentiation. So here is my derivative, which is really nice, and I can look back up at the information that I laid out at the very beginning of my problem, and now I should be able to just take all of that relevant information that's really easy to identify and plug it into my derivative that I have right here. So 1 times dA over dt, that's just going to be dA over dt. And we said that's what we're solving for, so we'll just leave that as dA over dt is equal to 2 times pi. Remember, pi is a constant. R in this case is 500, so we'll plug in 500, times dr over dt. We were told that was 0.32, so times 0.32. And in this case, we don't really even need to do any algebra. We just need to multiply out that right-hand side. So 2 times pi times 500 times 0.32, I end up with dA over dt is equal to 1005.31 if I round to 2 decimal places. So this is the derivative of area with respect to time. I can look at it first of all and say that is a positive number, which means that the area of this spill is increasing. And that makes sense. If the radius is increasing, then the area of the circle also has to increase. But I do want to make sure that I give a unit here. So I'm going to look first of all at what are the units of area. I can look at this problem and I can look at how radius was measured. Radius was measured in feet here. But remember, area is two-dimensional. It's not just one-dimensional. So I need to say not just feet, but I can say either square feet or I can say feet squared, whichever you prefer. So the units on A would be square feet per what is my unit of time. That I'm going to look back at my problem. We were looking earlier at feet per minute, so that means minutes is our unit of time here. So the unit on our answer is going to be square feet per minute. So if I wanted to summarize what's going on at this particular moment in time, I could say that the area of our spill is increasing by 1005.31 square feet per minute.